Welcome to part 3 of our mathematical dive into waves. In the last part, we discussed the possibility of finding a solution to a non-homogeneous differential equation, such as the three-dimensional wave equation with source, via some sort of inverse to the differential operator. We were left wondering how to construct a method for finding such inverse operators. Motivated by this question, we will rediscover the Dirac delta function, Green's functions, and convolution. And then we'll bring these three important ideas together to discover that elusive method for finding inverse differential operators. This video is a long one, but I promise you that the beauty we're going to discover along the way will be absolutely worth it. Let's suppose that we have a mass whose movement is restricted to one spatial dimension. To keep track of its position, we'll specify an origin point and label the sign displacement of the mass from the origin point as y of t. And so, we'll suppose that the mass's motion y of t satisfies some sort of linear differential equation in t. We can write this as a differential operator d, which we're assuming is linear in t, acting on the position y of t, as equal to some sort of force function, f of t, that's being exerted on the mass. And if d is a differential operator that is linear in t, we can write d as a sum of partial derivative operators in t multiplied by coefficient functions a sub n, which are functions of t. We want to solve for the position y, given any force function f. Let's consider this arbitrary force function. Well, how about we think of the force as a sequence of little kicks, impulses? The motivation for this is that if we know how a system responds to a kick, then we know how the system would respond to any force, as any force would be nothing but a sequence of these kicks. In the limit of this idea, each kick would in some sense represent infinite force over zero time. So let us sort out what a force function for the kick should be. To make this a little simpler, let's assume that the kick happens at t equals 0, for we can always shift the argument of the kick force function to make the kick happen at a different time. And let us also set the total imparted momentum by the kick to 1. This can always be changed by scaling the kick force function. So perhaps the kick force would look something like this, where it's centered around t equals 0. And we require that the total imparted momentum by the kick is 1. That is, that the integral of the kick force, f sub k, over all of time, that is, the limits go from negative infinity to infinity, is 1. So one way to construct such a function would be to say that the kick force is equal to 1 over epsilon when t is within epsilon over 2 of 0, and 0 otherwise. This would give us the large force that we expect from a kick around t equals 0, and, if epsilon is very small, for short time. And you can check that the integral, which is just the area under the graph in this case, is equal to 1. As epsilon approaches 0, f sub k becomes more like a kick, or an instantaneous impulse, which is what we were looking for. And so we can say that the instantaneous unit impulse force function is equal to the limit of this f sub k when epsilon approaches 0. And we've just discovered the Dirac delta function, which is the function in this limit. So the Dirac delta function represents the instantaneous unit impulse force, as desired. So the Dirac delta function, delta of t, is 0 for all time, except at t equals 0, where it's infinite. And infinite in such a way so that the integral of the Dirac delta function over all time is equal to 1. We've seen one way to define the Dirac delta function, and that was the limit as epsilon approaches 0 of our function f sub k, illustrated here on the left. But there are many ways to define the Dirac delta function, all leading to the same infinite at 0 behavior. Another way would be with the normalized Gaussian distribution, where the standard deviation sigma approaches 0. Furthermore, we can consider the integral of the delta function, where we integrate from negative infinity up to the variable t. The integration variable here is written as t prime, so as to not confuse it with the limit. The result of this integral will be 0 for t less than 0, and 1 for t greater than 0, because then we would be integrating over that spike at t equals 0. This happens to be the definition of the Heaviside step function, and so another way to define the Dirac delta function would be as the derivative of the Heaviside step function. So let's now explore some properties of the Dirac delta function, and here we'll be using the variable x instead of t to make this a little bit more mathematical. So we already know that the integral of the delta function over all x is equal to 1. But what if we integrate the Dirac delta function multiplied by some function f of x? Well, we can Taylor expand f of x in x about 0. Here we've written the 0th order term, f of 0, and grouped all terms of order 1 and higher into the big O notation. Splitting this integral into two as follows, we see that the integrand in the second integral will always be 0, because if x is non-zero, then the delta function delta of x is equal to 0, and if x is equal to 0, then all the other terms are equal to 0, which are multiplying the delta function. This might be a bit confusing, because the delta function is infinite at 0, but remember that the delta function really stands for a limiting process, so at all stages of the limiting process, the delta function is actually finite at 0. Thus, this integral comes out as 0, and so we can ignore it. In the other integral, f of 0 is just a constant, so we can pull it out to the front, and we already know that the remaining integral evaluates to 1. And so integrating delta of x, multiplied by some function f of x, over all x, gives us the value of the function at 0. But what if we consider the delta function shifted by some amount a? Well, in this case, we can perform the substitution u equals x minus a, so as to bring the argument of the delta function back into its standard form. We see that this reduces to the property we just looked at, except instead of f of x, we have f of u plus a, with u playing the role of x. And so this is equal to f of 0 plus a, or just f of a. And so in this sense, the delta function has a sifting property, where it sifts out the value of f at a if you multiply the function f of x by delta of x minus a, and then integrate. Finally, notice that the delta function is symmetric about 0, and that the delta function of a times x, where a is a constant, is equal to delta of x divided by the magnitude of that constant. These I will leave as an exercise to prove, and proving them amounts to considering how they act under the integral sign when acting on a function. Remember that the Dirac delta function has little meaning when it's not under an integral sign. So far, we've been thinking of the Dirac delta function as a mathematical peculiarity with some interesting sifting properties, or, more physically, as an instantaneous unit impulse force, a kick. But there's another important physical way of thinking about the Dirac delta function. Suppose we have an eternal point charge of charge q sitting at the origin of some Cartesian coordinate system xyz in 3D space. We ask, what is the electric charge density ρ of this space? The total charge over all space would be the volume integral over the charge density ρ. This would be a triple integral over the three coordinates x, y, and z, and over the volume that is all of 3D space. This must be equal to q, since the point charge is the only charge in all of space. To ease the notation a bit, I'll rewrite the triple integral sign as a single one. This is not ambiguous, since the volume we are integrating over is three-dimensional. I will also write the coordinate triplet x, y, z as r vector, and the three-form dx, dy, dz as d cubed r vector. So we require that this condition holds. But there are no charges out with the origin, so the charge density out with the origin must be 0. So for this integral to evaluate to something other than 0, we require that the charge density is infinite at the origin. This looks awfully reminiscent of the Dirac delta function, but in this case, we need something three-dimensional, like a three-dimensional Dirac delta function, not a one-dimensional one. How about we just consider the product of three Dirac delta functions, one for each coordinate axis, where we also multiply by q to ensure that the volume integral will come out as q, not 1. We also see that, correctly, the only place where the charge density has a non-zero value is at the origin. We will rewrite this product as delta cubed of r vector. We use this notation exclusively for the three-dimensional delta function relating to the Cartesian triplet xyz, as written here. And so, we suppose that this is the charge density distribution for a point charge q at the origin. To check if this is right, we can try plugging it into the volume integral. We can pull out q because it is constant, leaving us with the triple integral over the three-dimensional delta function. And I'll leave the details to you, but this indeed comes out as 1, giving us the total charge in space as q, which is exactly what we wanted. So delta functions in higher dimensions are actually products of the good old standard delta function. So now we return to the equation of motion that we were trying to solve for an arbitrary driving force function f of t. We thought that if we knew how the system would respond to a kick, then we could figure out how the system would respond to any force, since any force could be thought of as a sequence of kicks. So now we pose the question once again, How does the system respond to a kick? Well, we now know what the kick is, mathematically speaking. If we let f of t equal the delta function of t minus t prime, this would represent a unit impulse applied at time t equals t prime, the so-called kick. So let's say that the function g of t prime is defined as the solution to the differential equation d acting on g t prime equals delta of t minus t prime. That is, we'll define g of t prime as the system's response to a unit impulse applied at time t equals t prime. This function g of t prime is called the Green's function for the operator d centered at t prime. Notice that this function is defined only by the differential operator. In the case where t prime equals 0, we'll simply write g of t and call that the Green's function for d, as opposed to the Green's function for d centered at 0. So unless we mention the point about which the Green's function is centered, we mean this single input Green's function. And so clearly, the Green's function for d satisfies the differential equation where d acting on that Green's function gives back the delta function. So g represents the system's response to a unit impulse given at time t equals 0. The reason we omitted the t prime is because we guessed that the universe should not care on when we apply the impulse. In other words, it may be the case that d acting on g of t minus t prime equals delta of t minus t prime. That would be very convenient, because then g would only need to have one input, not two. So when is this the case? What constraints must we have on d for this dream condition to hold? We recall that d is a linear differential operator in t, and so we can express it as a sum of partial derivative operators in t multiplied by coefficient functions in t, labeled here as a sub n. All this t-dependence suggests that we can write the differential operator as a sort of function of t itself, and instead of saying d of t, I will be pronouncing this d in t, to help separate this from the traditional function of t. This t relates to both the argument of the coefficient function and the variable of the partial derivative. So we know that d in t acting on g of t equals delta of t, and so simply shifting the arguments to t minus t prime, we have that d in t minus t prime acting on g of t minus t prime is equal to delta of t minus t prime. But the dream property that we wanted was that d in t acting on g of t minus t prime is equal to delta of t minus t prime. And so from here we see that it is sufficient if d in t is equal to d in t minus t prime. That is to say that d should be translation invariant. The differential operator should not change over time. Well, what does it take for d to be translation invariant? We first substitute in the series expressions for the differential operator. We can write the partial derivative operator in t as equal to the derivative of t minus t prime with respect to t multiplied by the partial derivative operator in t minus t prime by chain rule. This derivative evaluates to 1, and so we see that the partial derivative operator is translation invariant, and so it follows that the nth partial derivative operator is also translation invariant. So, for the dream property, it is sufficient for the coefficient functions to be translation invariant. That is, each of these functions is actually a constant. And so, if the differential operator takes the form of a sum of partial derivative operators with constant coefficients, then the dream property holds. If d is of this form, then d is linear and translation invariant. And it just so happens that all the differential operators in the series will be linear and translation invariant. And so we need not consider the old notation where we wrote g of t prime, and instead we will always write g of t minus t prime. So we will forget the old notation, and from now on, whenever we see a Green's function with two inputs, that will mean that it's a two-dimensional Green's function, that is, a Green's function for a two-dimensional differential equation. Thus, for a translation invariant differential operator d, we only need to find the system's response to a kick at 0, since the system's response to a kick at time t prime would simply be that response but shifted by t prime. And so we only need to find g of t. So let's find such a Green's function. Recall the driven oscillator that we saw in part 1 of this series. The displacement from an equilibrium position y of t of a mass on a spring would satisfy this differential equation, where f of t is the driving force. We assume unit mass here. Our Green's function will satisfy the equation when the driving force is that kick, delta of t. Let's apply the operator to g of t. Then we see that, for t less than 0, delta of t is 0, and so the Green's function in that region would simply be the homogeneous solution, which we can write as c1 times sine omega t plus c2 times cosine omega t, where c1 and c2 are some constants. And similarly, for t greater than 0, delta of t would still be 0, and so the Green's function would also be some homogeneous solution. In this case, we'll use different coefficients, and it will equal c3 sine omega t plus c4 cosine omega t. So the Green's function g of t for the operator d2t plus omega squared will equal the following. We now want to find what the coefficients must be, and for this, we'll need some help from initial conditions. Let's assume that the mass was stationary and at the equilibrium position before the hit. This will ensure that the system's response to a kick will only happen after the kick has occurred, not before. That is, we want a causal Green's function. We don't want future events to affect the present. These initial conditions tell us that the constants c1 and c2 must be equal to 0, and so the Green's function will equal 0 before the kick. Now, we know that g of t satisfies the differential equation where the second time derivative of g plus omega squared times g is equal to the Dirac delta function. Integrating both sides of this expression between negative infinity and t gives us the following. The second time derivative is now the first time derivative, and the second term involves an integral. The right-hand side has become the Heaviside step function. The Heaviside step function has a discontinuity of 1 at t equals 0, and so we require the same from the left-hand side. The left-hand side must have a discontinuity of 1 at t equals 0, and if we can find constants that ensure this is the case, then the differential operator acting on our Green's function will give us the desired Dirac delta function property. Now we know that the mass can't teleport, so g must be continuous, and since we know that g is 0 for time less than 0, this means that the limit of g of t, as t approaches 0 from the right, must be 0 also. This tells us that the coefficient c4 must be equal to 0, and it also tells us that the integral of g must be continuous, and so the integral term does not contribute to the discontinuity. Thus, the discontinuity must come from the derivative of g, and this makes sense because kicking the mass should instantly change its velocity. By the initial condition, the limit of the derivative of g as t approaches 0 from the left is equal to 0. And so for a discontinuity of 1, we require that the limit of the derivative of g as t approaches 0 from the right is equal to 1. And this implies that the coefficient c3 equals 1 over omega. And so plugging these coefficients in, we find that the Green's function, subject to causal boundary conditions, will be 0 for t less than 0, and sine omega t divided by omega for t greater than 0. In plotting this, we see that this looks exactly how we would expect. The mass is stationary until we give it a kick at t equals 0, at which point it starts oscillating. So we've been looking at Green's functions for differential equations in one variable. But what about differential equations in multiple variables, such as the three-dimensional wave equation? Here, W3D is the three-dimensional wave equation operator, u is a field, and ρ is a source, and we use r vector as a shorthand to denote the coordinate triplet xyz. Remember that the Laplacian is the differential operator that is d2x plus d2y plus d2z. So this is a differential equation in 4 variables, as opposed to 1. So we naturally define the Green's function for the three-dimensional wave equation operator as the solution to a delta function source, and in this case, the delta function source involves 4 variables, and so it's the product delta of x times delta of y times delta of z times delta of t. And we give this Green's function a special name, G3D, where once again we've used r vector in its argument to denote the coordinate triplet xyz. So here, in yellow, we have the source. The source only has a non-zero value, where it's infinite, at one point in space and time, that is, at t equals 0 and at the origin of our coordinate system. We imagine that a causal Green's function would be 0 before the delta function source, and after which a disturbance would propagate spherically outward. This Green's function would be based on causal initial conditions, but we could equally impose anti-causal initial conditions, where the Green's function would be some sort of disturbance propagating inwards towards the origin, at which point, at t equals 0, it would vanish. In this case, the delta function source would be affecting the past, not the future. This is unphysical, so generally we imply that a Green's function is causal. And I'll leave it to you to check that W3D is translation invariant in space and time. So our fundamental Green's function solution will lend itself to any instantaneous delta function source anywhere in space and time. The great insight that Isaac Newton had when dealing with gravity back in the day was realizing that the laws of physics up in the heavens were the same laws as those down here, which is a statement about translation invariance. And here I have the differential equation that the gravitational potential field phi satisfies, and the source term on the right-hand side is 4 pi times Newton's gravitational constant times mass density rho. The important part here is that the Laplacian is the differential operator, and that it is, indeed, translation invariant. Let's step back a bit and recall the Dirac delta's sifting property, which says that if we take a function f of x and multiply it by the Dirac delta function delta of x minus a, and then integrate over all x, we get the function f at the point a. But we can think of the left-hand side as a way of combining two functions, in this case f and delta, and this combination ends up being a function of a, in this case f of a. More generally, we could think of this combination between functions f and g, where f and g are any functions such that the integral is convergent. This integral itself is some sort of function of a, so let's denote it f asterisk g of a, where the asterisk, which instead I will call star because it's easier to pronounce, denotes the operation of combining the functions f and g. If we want to think of the operation as a closed one, meaning it takes functions from a certain function space and then back to that function space, we could think of f and g as being functions of a, and write this as f of a star g of a, where the star is the operation once again. And sometimes I'll be lazy and simply write f star g. Now here a is the variable, which might be misleading because often a is constant. So let's relabel these variables, rewriting a as x to imply that it is a variable, and let's relabel the integration variable x as x prime so that we do not confuse it with the now new variable x. And what we have is a way of combining two functions, f and g, which are both functions of x, to produce a new function of x, f star g. It would be awfully convenient if f star g was equal to g star f, that is, if this operation was commutative. So let's check if this is the case. F star g is equal to the integral of f of x prime multiplied by g of x prime minus x dx prime. Using the substitution u equals x prime minus x, and working through the details, we see that this is equal to the integral of g of u multiplied by f of u plus x du. Relabeling u to x prime, we can see that clearly this is not the same as g star f, because of this sign. So this operation does not commute. But how about we redefine this operation where we change the order of subtraction in its definition? Then, if we look at f star g and do the substitution u equals x minus x prime, and working through the details, we find that f star g is equal to the integral between infinity and minus infinity of f of x minus u times g of u multiplied by negative du. We can use the negative sign in front of the differential to flip the integration limits, at which point we realize that this is indeed the definition of g star f. And thus, with this new updated definition of the operation, we have one that is commutative. So this operation is called convolution, and the function f star g is called the convolution of f and g. So we already know that convolution is commutative, and, due to the sifting property of the delta function, we see that f convolved with delta returns the original function f. And so delta is the identity of this operation, which is partly what inspired us to pursue this definition. And as an exercise, I'll let you prove that convolution is associative. Now it is pretty hard to visualize this operation, but my best way to try to do so would be to picture two functions f of x and g of x, and then, reflecting g of x about 0, and shifting it to the right a units, we see, from the definition, that f star g of a gives us some sort of inference as to the overlap between the functions. In this sense, convolution is the mathematical process of blurring. And so many filters you'll see on cameras, and sound effects, will use convolution to blur images or sound. For functions with more than one variable, such as f of xy and g of xy, their convolution follows a very, very similar definition, Here we convolve over both variables. And in this case, the identity element would actually be the two-dimensional delta function in x and y, which is delta of x times delta of y. When I don't specify the inputs to functions, and write the convolution symbol, this would represent a convolution with an arbitrary number of variables, and in the same context, when I write a delta, that will stand for the identity for the convolution in that number of variables. So now we've developed all the necessary machinery to tackle those inverses to differential operators. At the beginning of this video, we looked at the differential equation representing an equation of motion, where d, a linear and translation invariant operator acting on a function y of t, is equal to some force term f of t. Now let's consider what happens when we apply this linear and translation invariant differential operator to a convolution between f of t convolved with g of t. Writing the operator d as d in t, and using the definition of the convolution, we can see that we can interchange the order of integration and differentiation because t and t prime are different variables. And furthermore, in the integrand, g is the only function with t dependence, and so we can pull f of t prime out of the operator. But d is translation invariant, so we can write d in t as d in t minus t prime. And we see that this is equal to the convolution of f of t and the differential operator acting on g of t. So we see that linear and translation invariant differential operators acting on a convolution can be passed into one of the convolved components, in this case g of t. Keeping this in mind, let's rewrite the differential equation as d acting on y of t is equal to f of t convolved with delta of t. If you recall, we said that we might be able to think of a force as a sequence of little kicks, or instantaneous impulses, and it is in this sense that we mean that. F of t convolved with delta of t is the lens through which we can view the force as a sequence of impulses. But delta of t is exactly the differential operator acting on the Green's function g of t, and, by the work we just did, we can pull this differential operator out of the convolution. And so now we see that d acting on y of t is equal to d acting on f of t convolved with g of t. And so we conclude that y of t is equal to f of t convolved with g of t. So it is in this sense that we can think of y of t as a sequence of responses to little impulses for any force function f. And this is absolutely incredible, because it means that as long as we know the Green's function for a differential operator, then we know the particular non-homogeneous solution to a corresponding differential equation using that operator. And I will mention that the initial conditions of y of t are inherited from the initial conditions of g of t, which we typically assume are causal. To see an example, recall that for the differential operator d2t plus omega squared, which was that for a harmonic oscillator, the causal Green's function g of t was given as 0 for t less than 0 and sine omega t divided by omega for t greater than 0. And so then, for the corresponding non-homogeneous differential equation, the solution y of t will be equal to the convolution of f of t with that Green's function. And, since g of t is only non-zero for positive inputs, in which case it is sine of omega t divided by omega, we can rewrite the solution as such. And so, let's consider the general differential equation d acting on u equals rho, where d is a linear and translation invariant differential operator. Here, this differential equation may be in any number of variables. We can write rho as the convolution of rho and delta, and then write delta as d acting on the Green's function for that operator, g. Then, since d is translation invariant, we can pull it out of the convolution, and then conclude that u is equal to rho convolved with g. And this shows d inverse can be written as the convolution operator with convolution kernel g. And so now, once we find Green's functions to the wave equations, we'll be able to find solutions to wave equations using this inverse differential operator. And that is the end of this episode. In the next part, we will derive the Green's functions for the Laplacian, Helmholtz, and three-dimensional wave equation operators. Thanks for watching, I hope you enjoyed.